talk about why we did some of the things we talked about. First, voltage, potential difference. If you apply a potential difference to a region in space, you create an electric field in that space. I don't know if you have that so plainly in your notes, but it would probably go a long way if you did. Again, if you apply a potential difference to a region of space, you create an electric field in that space. Now, you have to have a means in which to apply that potential difference. Something that you can do. There are several ways to do so, and we've talked about them, but you probably don't see it that way. The easiest way to apply or create a potential difference is to somehow distribute separation of charge, to place a buildup of one kind of charge or another in space. That's how you create a potential difference, and that will create an electric field. So an example of that would be to maybe take not a random piece of metal, maybe take something to which you understand how the electric field behaves. So maybe I'll take 2 sheets of metal, something flat and big, so that I can treat them almost like an infinite sheet. And maybe I'll place them close enough together where their areas overlap quite a bit, and the electric field produced by one sheet is complementary to the electric field produced by the other. Meaning, I take charges off of one sheet, place them on the other, creating a positive side and a negative side. This will, of course, charge up the 2 sheets. So let's say let's just pluck one electron off of the sheet to the left and place it on the sheet on the right. If I do that, the sheet on the left becomes positively charged. The sheet on the right becomes negatively charged. We use Gauss's law to come up with an expression for the electric field near a sheet of charge. I don't have to redo all of that to know that the electric field near a sheet of charge looks like this. How's that string?
Sorry.
It's not quite a fidget spinner, but it's fun.
No,
Is your plan to hang your water bottle from it?
I'm trying to make a lasso.
I had a feeling.
I did. Oh, I'll get back to it. I'm sorry.
Okay.
What's the potential?
We don't know yet. I don't mean that in a negative way. I'm getting to that. I know that electric field, though, will exist. Now, this is the electric field near a charged sheet. If we look at the sheet on the left, it will have an electric field that radiates on both sides, like so. And the sheet on the right also will have an electric field given by this same function. And the sheet on the right will have an electric field like this. Notice, in between the plates, the electric field is complementary. But outside the plates, the fields cancel. Meaning, the electric field from the right sheet looks like that, really. And the electric field from the left sheet looks like that, really. If the sheets are fairly close together, this blue arrow, which represents the sheet on the right, would cancel out with the electric field being produced by the sheet on the left, outside the sheets. And I have a similar cancellation on the right side when I'm outside the boundaries of the sheets. But inside, they're complementary. Yep.
Is the red from the left sheet?
Is the what?
Is the red arrow from the left sheet?
Yes. Yes, sir?
So, you know how the electric potential for a point charge is similar to how you write the electric field, just without like the extra R on the bottom.
Mm-hmm.
Is that just a coincidence, or like, is that a recurring thing for all of the shapes? Because I feel like if you follow that logic, would the potential be like sigma R over 2 epsilon naught, or is that just a pattern that I'm trying to look at?
You're trying to create a pattern that doesn't exist. Okay. It's just the only way to combine the numbers, I guess. Now, I do have a goal here, so I'd like to press on, and I'm talking slow and deliberate on purpose. It's because you guys complain, A, I talk too fast, and more importantly, I want to make sure you're catching all this, so I don't have to go back and repeat myself. You should know where these came from. I don't know how to directly apply them here yet, because the top number, sigma, is the charge per unit area of the plate. So the area of the plate probably has something to do with this. I just don't have that information yet. I haven't presented it. But between the two plates, the two contributions to the electric field are complementary. So between the plates, the electric field will be twice as large, because I have a created electric field from the left plate and a created electric field from the right plate. Now, all of this was started because a potential difference had to be applied between the plates to move some charge from one plate to the other, creating this concentrated electric field between the plates. This is, in essence, how a capacitor works. Now, when we here this conversation yesterday, I indicated that the potential difference can move charge. The charge, therefore, can create electric field. Once you have the electric field in place, there's energy there. And we used those two pieces of metal as a means to start. What I'd like to talk about today is how this definition of capacitance, which involves two specific ideas we developed early in the year, can be used to help us figure out how to construct an actual capacitor. Now, what I want you to understand, the takeaway of today, is that when we're done, you should be able to design a capacitor, choose specific features for its size that would help increase or decrease the amount of capacitance it has. Right now, the only way to measure the capacitance is to have two physical pieces of metal to which you could apply a potential difference of known quantity, and you would have to measure how much charge was moved to be able to determine the capacitance. That's a heavy lift, because I don't know that you guys would know how to do that. When we're done, we're going to have an expression for the capacitance that will have nothing to do with voltage or charge, but will have everything to do with its physical shape and size. That's our goal, to come up with a way to design a capacitor. Now, just so you guys know, before we get started, there are only 3 kinds of capacitors. Although I said any two pieces of metal can be a capacitor, that is true, but they don't have very much capacitance. If you want to design a capacitor, you try to design it in such a way that you have control over its capacitance. Therefore, we have 3 basic types of capacitors. There is the parallel plate capacitor. It is exactly what it sounds like it is. 2 large parallel plates. And it uses the idea of the electric field of an infinite sheet. So parallel plate, and it uses what we derived for an infinite sheet. There's a coaxial capacitor, or cylindrical capacitor. It's exactly what it sounds like. It's a small cylinder wrapped inside a larger cylinder. It uses the infinite line. Now, as capacitors go, sometimes you have capacitors that you design, sometimes you have capacitors that exist that perhaps you wish didn't. This is that second version. Every coaxial cable. Do you guys know what a coaxial cable is? But unfortunately, this kind of capacitor exists, often unintentionally. And that's a spherical capacitor. You can imagine why a spherical capacitor might be the worst kind of capacitor out there, because it's a isolated sphere in the center, surrounded by a sphere on the outside. How do you charge it up? Right? If it's an isolated sphere in the center, surrounded by a conducting sphere on the outside, you got to move the charges from the inner sphere to the outer sphere. So as a capacitor goes, it might be the least interesting or the least kind of capacitor you'd ever want to actually make, because it'd be difficult to construct. So from order of importance, the top one, the most important one, parallel plate capacitors, how every capacitor is made. We use parallel plate capacitors almost exclusively. We don't make cylindrical capacitors. They tend to be made for us. What I mean by that is they show up in nature because you can make a spherical capacitor under very special conditions. And usually when you do, it's accidental. And that thing, when it charges up and then discharges, often does so in an unpredictable way. And so we'll talk about some spherical capacitors that are like that. So here's how we're going to progress. In order to figure out how the shape of these capacitors determines capacitance, we use the definition of capacitance. Now, this is going to be a heavy lift for some of you, so I want you to pay very close attention to what I'm about to say. It's a couple steps, 3 of them actually. And here's what we do. Step 1, over here, 3 types of capacitors, because we did the Gauss's law for 3 different arrangements, didn't we? A sheet, a line, and a sphere. It's for this problem specifically. You want to create the condition for the capacitor. You want to create the condition for the capacitor and establish its charge. That statement doesn't mean a lot until I provide context. I'm not going to write down all the context, but you should. So here's what I mean by it. What kind of capacitor do you want to make? I want to make a parallel plate capacitor. So what conditions would have to be satisfied for us to use a parallel plate capacitor? Well, I want 2 big sheets of metal, parallel plates. So sheet number 1 and sheet number 2. Since I know a sheet creates a uniform electric field, I want to arrange the sheets so that they are parallel. That would provide the most uniformity of the electric field. You guys follow why I'm saying that? The electric field is perpendicular to the plates. If I arrange them parallel and I'm careful, then I should have a nice uniform field. I want the area of the top plate to overlap the area of the bottom plate. I know you think I'm just wasting my words here. I am not. The only place that will really matter will be where they overlap. We don't have the same electric field on areas of a parallel plate capacitor that don't overlap. I want as much consistency as possible. So I want to arrange it so that they overlap. And I want as much area to overlap as possible. I'm going to identify what I feel are probably important things about my parallel plate capacitor, like they're separated by a distance d. And the plate, although I've drawn this, so that we can just see down it, the plate has an area. I am imagining it's like a big square. And I'm just looking down along the square. But if you need, 3D, good luck with that. But making fun of my drawing.
People need 3D.
I got those boxing gloves in the back. I'll kick the crap out of you. There. Is that enough for you to get the image? Because I don't, that's distracting for what we wish to do next. So I just want you to understand, when we're talking about parallel plates, I'm quite literal here. That the plate is a sheet of aluminum foil and another sheet that is the same size and shape. Now look, here, I want to be very careful here, but I'm also trying to be direct. We want to be able to know what the electric field is in the space between the plates for what has to happen next. So I am attempting to control for as much of the shape and construction of the capacitor. I know that it's any two pieces of metal. But to understand why I'm being so careful here, you have to understand we are going to be doing work on trying to calculate how the charge on the plate creates an electric field. So the more uniformity we can grant the problem, the less work we have to do. So again, this is all distracting. I want to come back to this.
Can gold be capacitors? That's just like a quick question.
Any metal can become capacitors. Any conductor. Yes?
How do you tell it to discharge itself?
You don't,
Just two plates.
it's not sentient. You can't tell it to do anything.
Okay, well, like, control it, I guess.
Okay, let me direct the direction we're going for this, please. And then I'll be able to answer your question.
Excuse me.
Do the materials of the plate have to be the same metal?
No, they don't. But we are treating all conductors as if they are all the same for the time being. There is some reasons why you would choose one metal over another. But for right now, we treat all metals as if they are the same. Okay, so we have created the condition for the capacitor. Now, we want to establish its charge. This part's important. We are going to charge the capacitors, but we're not going to make a big deal about this. What we're going to say is, I'm going to remove an equal amount of charge off of one capacitor plate and place it on the other. You don't have to know how that's done, but I think you can imagine that if I connect a conducting pathway by using something like a potential difference, I should be able to drive charge from one plate to the other. All you have to be aware of is that if this is a true capacitor and you have access to the plates, I can charge one of the plates to be positive Q, and that makes the other plate negative Q. I move charge from one plate to the other. And Q is going to act as a placeholder for now, but it represents the charge on the plates. Are we okay with that? Good so far. All right, question 2, or point 2. We have now established the conditions for our capacitor. It's two plates. They are parallel. They have area A, separation distance D. That is the shape and size and construction of our capacitor. Now, here's the actual job. We know that capacitance is based on how much charge you get per unit voltage. We're going to work the problem backwards. We're going to say, I have charged the plates with a value Q. My next job is to find an expression for the electric field that exists due to the charge I've placed on the plates. Find an expression for the electric field due to the charge I've placed on the plates. You would usually use Gauss's law for this. Now, we've already done this problem, but I want to reiterate, we spent all that time learning about electric fields and stuff, so we don't have to do that work here. But if you wanted to, or if you were asked to do it on the test, and you could be, this would be where they would insert Gauss's law into your test question to say, using Gauss's law, find an expression for the electric field between the plates of a capacitor. And it would be your job to do that. Now, we've already done this. We know that the electric field between the plates of the capacitor, using Gauss's law, comes out to this. Or for a plate, it comes out to that. For this arrangement of two plates, it comes out to this. That was the whole. But a reminder that this expression came from doing Gauss's law on a single sheet of charge. Do you guys remember that a couple of weeks ago? I don't want to revisit that today. I want to say insert that conversation here, meaning remember that? We took a single sheet with charge Q, and we had the top, bottom, and sides. We said there was no flux through the sides. We did the top and bottom alone. Do you remember that whole conversation? That's how we came up with this. Oops. That's how we came up with this. So I don't want to revisit that. It's in your notes already. But step 2 on a test could force you to revisit this. Does everybody understand? But I want to keep going. We already know that is our standard form for the electric field between the plates, or near a sheet. Do you understand now? Now, I'm going to keep going because the next part is important. We haven't actually done what this says. We're close. If we did Gauss's law correctly and we got an expression, our expression is in terms of the charge per unit area. We know that the electric field is sigma over epsilon naught because there are, two plates. So it's twice the electric field, one for each plate. But this is not in terms of the charge on the plate. So I would have to replace sigma with charge per unit area so I can work in the charge on the plates, which will work out to be charge per area times epsilon naught, where area is the physical area of the plate. Its length times its width.
What is Q over A stand for? Charge over area?
Yes. We still good so far? Is everything all right? Because the last step is not hard, but again, it's all the pieces. Next, we want to figure out what potential difference exists from one plate to the next based on the electric field that's been produced by the charge. I'll make this all smaller so I can write that in there. 3. I want you to determine the potential difference from the electric field produced by the charge. Stop it. Oh, wait, no, I allow one freebie. It's the next one where I say stop it. So you got your one freebie.
He said thank you, by the way.
So this part, it's the same formula every time. You're just going to use this. Oops, I put A there, but it should be S. Sorry. We have an expression for the electric field. We just need to integrate from one plate to the next. And generally, this is pretty easy. It's just that there's a lot of steps here. Now this one we haven't done yet. So this is one is new for us. We're going to go ahead and perform this step because it's really easy. We ready to go? We're going to go from the negative plate to the positive plate, going from the area of low potential to the area of high potential. We know that there's an electric field that way between the plates. And we know the electric field is this. Those are all the things we know. So the potential difference has to be the integral of the electric field dot ds. The electric field is down, but we're moving upwards. So the dot, there's a negative sign out front. So the dot product is going to be the cosine of 180 degrees. Again, once we get to the end of this process, largely not necessary. But it is plausible you might have to do this. We have an expression for the electric field. Oops. I'm going to change it from ds to dy because we're moving in the vertical direction. So if I was to put a little x and y here, this is for me to make sure we understand that ds is a placeholder for moving from one point in space to another point in space. I'm moving in the y direction. And I'm going to set my limits. I'm going to start at the bottom plate and call that 0. That's my low potential. And I'm going to move to the top plate a distance d away. I said the plates are separated by a distance d. And this should give me the potential difference between the plates based on the electric field. Now, hopefully you note that everything in this integral is a constant. Q doesn't change as I move from one plate to the other. Epsilon naught doesn't change as I go from one plate to another. And A doesn't change as I go from one plate to another. Those are all fixed quantities. The cosine of 180 is -1. So this whole thing becomes Q over A epsilon naught and the integral from 0 to D of dy. Now, I do expect you to do this calculus because this is just the integral of 1 with respect to y, which means it's the integral of y to the 0 power. Do I have to go through all that whole rigmarole again to prove to you that the antiderivative of 1 with respect to y is just y? So is that okay? Is that not okay? That's okay? All right, we're almost done. So, we have that the potential difference across a capacitor is Q over A epsilon naught times D. Yes, sir.
Isn't that what I said earlier? Like I was asking.
Questions. I want you to understand. But I'm just just seconds away from the answer. What I really wanted to show. We have an expression for the electric potential. We proved the expression for the electric potential based on charging our plates. We worked backwards. We said if the plates had a charge, they would create an electric field. If we found the potential created by this electric field, we could find an expression to show us what the potential is between the plates. That's this. But go back to our definition of capacitance. Capacitance is how much charge do you get for an applied potential? How much charge is moved when you apply a potential? Now, we had a specific arrangement. In this arrangement, when you can move this much charge, the potential that you would get looks like this. Now, this looks complicated, but pay very close attention to this. We can make this simpler looking. If you look closely at it, I can multiply that on the top and bottom to get rid of this compound fraction. And there's a Q on the top and a Q on the bottom. They cancel out. And what it produces is an expression for capacitance that tells you how to build one. Right? If I want to build a capacitor, its capacitance is physical. It has physical properties. If I want to make it bigger, increase the area of the plates. Get the plates as close together as possible. That will make a bigger capacitor. It's that simple. A capacitor is a physical device that stores an electric field. That electric field stores energy. And we now have the physical parameters to make one. It's very clear. It's very straightforward. The only problem is it has some limiting functions. This value here, the permittivity constant, assumed that we had a set of parallel plates that had nothing inside of them. It's hard to do that.